Okay, hello everybody, and welcome to everyone who comes in and also anybody who ends up watching the recording. So, we're going to do a Taurus report today on all of the things that have happened. I mean, it's been months since we've had a show, but a lot of stuff has happened in the news, and I'd like to one by one go through each of these things just to say what impact it has on cosmology at present, and what challenges to current theory there is, and what I think the solution to those problems is. And feel free to put any questions in the chat. And the first thing I would actually like to take a look at is a recent development. And at first glance, this does not have much to do traditionally with what people would think of as cosmology. Now, I think it does because I think it gives a clue to what a valid theory of gravity would be, which I don't think that general relativity is correct. And this thing that is happening right here in our local solar system, I think gives a hint about what gravity should be, what the theory of gravity should be. So, what I would like to do is just first give a little background on this idea, and it has to do with comets. So, like if here's the sun, now typically planets, our orbits are roughly circular, not exactly a circle. It's called elliptical, so technically it's an ellipse. But I mean, most of the planets are pretty close to a circular orbit. Comets, however, when they come in and they have very eccentric orbits like this. And these eccentric orbits um, cause them in my theory, in CGC, cyclic gravity and cosmology. My theory predicts that gravity at various points, as you get further and further away from the source of gravity, which in this case is the sun, gravity at certain points will deviate from what is expected. And my theory explains, all about that. And I'll put links in the comments. So this all deviates from what is expected. Now, in circular orbits, this does not show up because whatever the force of gravity is constant. And so it's going to stay operating in the same way. So anything in a roughly circular orbit, these sort of microscopic accelerations or decelerations will not show up because gravity doesn't deviate in a circular orbit. Now, with comets, we do get this. And then I welcome uh, Lee, my friend Lee. I welcome him back, and we will continue.
Yes. Yes.
So, anyways, as I was saying, with comets, it was found that they do have minute accelerations and decelerations.
Mhm.
And standard theorists, the way that they dealt with that issue, because this is not predicted by either Einstein or Newton in their theory of gravity, and they had to deal with it in some way. So they assumed that comets, how comets have tails of stuff that they're off gassing. And so they would say that the reason why comets have these unexpected accelerations and decelerations at certain places in the orbit is because of the off-gassing of material.
Mm.
And so that is why comets traditionally are viewed to have this. Now, in CGC and in the paper that I have published on that, and I will again include a link to it, okay, in Chasing Oumuamua. So this is the paper. And if in this paper, which I published several years ago, I made the statement that this movement of comets was not due to off-gassing. And so, yeah, so here in the paper in section 8, I discuss all of that and say it is not due to off-gassing. And I said if we have some meteorite or something that is not off-gassing material, like let's suppose on this kind of a path, this very elliptical path, if you do not have off-gassing material, I said that you would observe these same uh, minute changes in gravity because gravity has this wave-like characteristic. So in my theory, when I graph it, these wave-like characteristics, of course, are um, greatly exaggerated. Let's see if I can find. So,
That particular graph you just passed, I think illustrates that, doesn't it?
well, that is something a little bit different, which, I don't mind the digression. Okay. This is a group of astronomers who they analyzed the CMB and they said um, they, made this model. And sorry about the digression here, but it's actually quite uh, uh, surprising. So I don't mind kind of going into this digression. So these astronomers, they did an analysis of the CMB and they said, and they wanted to disprove the idea of modified gravity. Okay. So they said, if the CMB, if the anisotropies in the CMB under detailed analysis, if they were due to modified gravity rather than the stretching of space, as
Mhm.
Einstein says, then they said, look how ridiculous modified gravity, what it would have to look like. Okay. So they put it into their computer modeling system and they said, well, if the CMB is due to modified gravity, then this is what the gravity thing what the force of gravity would have to look like. And just so, everybody understands what they're talking about, the force of gravity, according to Newton and Einstein, looks something like this. Okay. Where very near, like if the sun is causing the gravity, very near to the sun, you have very high gravity. As you get farther away from the sun, you have very low gravity. And so the gravity curve, according to Newton and Einstein, looks something like that. Very simple, very straightforward.
Like a decay, basically.
Yes. Okay. Which, I mean, it makes sense. As you
Yeah.
get further away, it gets weaker. Okay.
Yep.
But the force of gravity is smooth like that. Okay. So these guys were saying if the anisotropies in the CMB were actually due to modified gravity, this is what the force of gravity would have to look like. And their intent was to disprove modified gravity. They're saying,
Right.
look how ridiculous gravity would have to look.
Right.
Okay. Now, according to the theory that I put forward here, let's see, I'm looking. Oh, here's mine. Okay. So this is what I say gravity looks like. Okay. And the planets in green, like here's Mercury, here's Earth, I'm sorry, Venus, Earth, Mars, Jupiter. Okay. Now I'm saying gravity is sort of like this blue line, and these waves are exaggerated. Okay. In this picture. So it's actually a lot smoother looking than this because I deliberately exaggerated the waves. Okay,
Hmm.
so I'm claiming there's imperfections in gravity.
Hmm.
And this right here, this little green dot right here, is the observed acceleration of Oumuamua. And so this is how my theory would explain to it that there's just a variation of gravity that would accommodate Oumuamua.
So
Okay. And
basically a statistically significant deviation from the simple decay pattern
exactly.
that you would expect. Yeah,
Right. Now, the theory that I'm saying, you still have a decay pattern because it obviously gets less as you get further away from the sun.
sure.
So there still is decay, but I'm saying there's slight variation. Hello, everyone. I just wanted to interject here. I was editing the video and I just wanted to make a comment about that. I said that the modeling that these scientists do was based on the fact of if the CMB was due to the stretching of space, and that's mistaken. I made a mistake there. What I was trying to say is, um, according to standard theory, the CMB has the anisotropies that it does have, and part of the explanation for why it has those, the structure it has, is they incorporate dark matter. And so I mistakenly in the video was talking in terms of dark energy, i.e., in other words, explaining it in terms of the stretching of space. In fact, those researchers, they did their modeling based on the idea of no dark matter. And they said if there was no dark matter in the universe, then the force of gravity, whatever theory we have for gravity, gravity would have to vary in this strange wave like way. And so they put that forward, basically trying to tell everyone, look how silly and ridiculous a graph of the gravitational force would be. Look how silly it would be if we try to model it without dark matter. And so that's what I was attempting to say, and I sort of misspoke in the video. So I just wanted to throw in this little edit. Thank you. Okay. And so in this paper, I predicted the fact that if we had meteors in the solar system that were
Hmm.
dark, in other words, just a lump of rock, no off gassing. And
Hmm.
I said that if you put them in an elliptical orbit like this, you would get these same variations that we see in comets. Okay, and
Hmm.
I put that in my paper. And now the article of interest that just came out recently. Now, in I was going to say the old days. That sounds kind of casual, but anyways, I'll just say it. In the old days, okay, we couldn't observe rocky meteors like this without off-gassing because they have no tail. It's not that easy to track, a tiny little meteorite or something in the
Right.
vastness of space. How do you track something like that unless it's glowing? So the only
Right.
thing we had to track in these super elliptical orbits was stuff that was glowing, stuff that was off-gassing. And so every time we tracked something like this, it had these subtle variations in acceleration. And scientists just always said, "Hey, that's due to off-gassing. That's why it is." Okay,
Hmm.
but now in these times, in this article here. That's what I'm trying to pull up. Is it this one? Yes. Okay. The astronomers are expressing confusion about this because now we have telescopes and computer programs advanced enough to be able to track rocks.
Hmm.
And some of those rocks are in big elliptical orbits like that, very eccentric orbits. And guess what they're seeing now with all of them? Okay. If they are in eccentric orbits, all of them are showing this same variation in acceleration, and they're calling it non-gravitational acceleration still.
Mm.
Okay, and so this article, which I'll link in the comments, this article is all about that. And they notice that there's a similarity to Oumuamua. And, Oumuamua, of course, was the first interstellar asteroid that passed through our solar system that we detected. I'm sure there were others, but that was the first one that we detected. And it also displayed what they called non-gravitational acceleration. And according to what I'm saying, there's nothing non-gravitational about it. It is gravitational. It's just that gravity does not behave the way that Newton and Einstein say it does. That's all.
Right,
And so
right.
these objects that are simply rocks, they're in positions where we have this sort of where gravity isn't behaving exactly as predicted.
Hmm.
So, and again, all of these articles we go over today, I'm going to link in the comments. So let me stop share. And so, Lee, again, welcome. And what would you like
Thank
to
you.
take a look at first?
Well, I mean, certainly I've been doing a lot of updating on the Enlightenment Legacy History of Cosmology website. Most recently, well, I'm getting ready to tackle the big chapter three. I've been doing a lot of other chapters, but this chapter three covers the years between the turn of the century and about 2013. That
Mhm.
period of time when there were controversies in the 20th century in cosmology. And and right now, what I've been most recently updating is is the chapter. I guess we could show my website or
Yeah,
whatever.
that'd be great. And again, I will put all these links in the comments for the video when I post it.
Right. So let's see. I can share here. So here we are. This is enlightenmentlegacy.net/cosmos, and basically, okay, just a second. There we are. Okay, and it and this chapter, well, coming down to the actual chapters, there's a lot of stuff happening. Of course, we're coming up on some more anniversaries of various discoveries in the early 20th century in cosmology. Here we are 25 years into the new millennium, the new century, right? And there's a lot of things that are happening. So anyway, this Hubble relation, well, now I have to actually adjust the title because it's formally called the Hubble-Lemaitre relation now. So that has to be updated. But right here on unexpected large red shifts, I've not only been dealing with the question of the Hubble tension, which has not been resolved. There were some very important papers and some very confident announcements made last year, and alas, the Hubble tension is unresolved. The Hubble tension between the standard measurements of supernova redshifts, the Hubble relation, of course, or the Hubble Lemaitre relation of kilometers per second per megaparsec, the supposed rate of the expansion of the universe.
Yeah,
Um,
supposedly constant. Yes.
Supposedly constant, although there are problems with that, of course, as we've discussed on this program before. Um, and what is measured from the cosmic microwave background. Well, there was some hope that maybe the tail end of the red giant branch might help, and alas, 'twas not to be. So, just gave another set of values that that were problematic. And then, of course, I've been going into the fact that there are intrinsic redshift issues. There are discordant redshifts. There are high redshift objects connected with with other low redshift objects. So that's what I'm in the process of updating now. There's a lot of material out there, and I'm in the process of updating that. So I guess
Okay.
I'll
So
stop
I'm
here,
going to,
Sharon. That's
yeah.
just a bullet, a quick whirlwind of some of the things I've been working on. Yeah.
Right. And so, what I'd like to do real quick is just for the audience, just to explain a little bit about the redshift and what all that means, and then I will link to uh, Lee's site, which is an excellent resource if one is looking for proof of the things I'm about to start saying here. Okay, so I'm going to
Right.
be saying a bunch of stuff and explaining how all this challenges standard modern cosmology. And then if someone wants the details and the proofs and the I guess we'll call it the real nitty gritty on observations of all this stuff, then Lee's site is an excellent resource for all that. And so I would like to just,
And a lot of the references in the literature too, which are so people can go and read the papers for themselves and see what's being argued about.
right, right. And so I want to explain just the basics of it to a layperson who, might not really understand what all this discussion about the redshift is. Let me see. I'm trying to get back to my, there
If
it
you want
is.
me to run a graphic up there, that might help that. I'd be happy to
Well,
do
I
that.
think I'm going to draw a little bit.
Yeah, yeah, absolutely. Absolutely.
Okay, so this is the basics of it. So Einstein, when he came up with his theory of general relativity, he realized a problem early on is that if gravity behaved in the way that he said it behaved, then eventually everything in the universe would start collapsing in upon itself. And given enough time, it all collapsed down to a single point. And so it immediately begged the question, if gravity is the only long range force that's exclusively attractive and it pulls everything together, then how did everything get spread out to begin with? And even once it is spread out, why doesn't it all just collapse back together, back into a single point?
Right.
And so the way that Einstein solved that problem is to tack on an arbitrary constant. When Lee was talking about the Hubble constant, that's basically what that is. Okay.
Hmm.
And this constant just says that the universe, the entire universe, and here we're talking about space itself, is expanding at a steady rate, at a constant rate. And the rate of that expansion is basically the Hubble constant. That's what we're talking about when we talk about the Hubble constant, is
Hmm.
the rate at which the universe is expanding, and it has to be expanding fast enough so that gravity cannot pull it back together. Okay,
Right.
um, so Einstein tacked on the Hubble constant onto his theory of relativity. Okay, now what does that mean going backwards in time? Okay, if you go backwards in time, the universe should be closer and closer. All the things in the universe should be closer and closer and closer together. And the further back in time you go, the more compact the universe is, the closer everything is together, until finally you get to what's called the Big Bang, which is the beginning of the universe. And so that is the, Big Bang, general relativity. We call it hot Big Bang, general relativity. And so to abbreviate it, sometimes in our papers and stuff, we say HBB, which stands for hot Big Bang, and
Hmm.
GR, which stands for general relativity. And so that is the basics of cosmology, just of standard theory. Okay, now what is this red shifting? I just want to talk about that real quick. So let me just draw a little bit to explain about what the red shifting is. And so red shifting is just like, if you've got some car and it's coming towards you and it honks the horn, right? And you're standing here. and it's driving fast towards you and you honk the horn, you get a very high pitched sound. Whee! Some high pitched sound. Now, someone standing back here, where the car is moving away from them, they get a very low pitched sound, right? Something like that. And all it means is that when for an object coming towards you, we will say when we're talking about light, we call this blue shifted because light waves, when they get compressed, they head towards the blue end of the spectrum. And light waves, when they get stretched, they head towards the red end of the spectrum. So this same idea, which I drew it as applied to sound, that same idea can be applied to, a star in the universe that we are looking at.
Mhm.
Okay. If the star is coming towards us at a fast rate, that star will be blue shift. If the star is heading away from us at a fast rate, that star will be red shifted. So when we're talking about red shifting, that's what we're talking about. Okay, the
Mhm.
fact that the stretching of light shows that stars are moving away from us. Yeah, well, what I should say is galaxies. Other galaxies, most other galaxies in the universe are moving away from us, and the further away they are, the faster they seem to be moving away. And I say seem to be because that's not necessarily the case in my theory, but um, because they're more and more redshifted. Okay, and so what happened in this last century is when astronomers started looking out into the night sky, they found something surprisingly. Um, if objects like galaxies were like randomly dropped into the universe and they were moving in all random directions, okay, what would we expect? We would expect some of them to be blue shifted, those that are coming towards us, and we'd expect some of them to be red shifted, those that are moving away from us. And what astronomers found instead was that nearly everything is red shifted, and the further away they are, the more red shifted they are. And so the universe seemed to be expanding at an increasing rate, so that the expansion is increasing. And all of this seemed to validate what Einstein was saying. Okay.
May I flash
Go ahead, please.
an image on really quick?
Sure.
Yeah. So for instance, here is the Doppler effect, like with a siren passing right here. The sound
Exactly.
as it passes you, and the same thing with light. So here's a picture from middle of last century of of a quasar 3C295, which is so far shifted into the red that these emission lines here are stretched out into these three lines here, which is the equivalent of a 41% shift toward the
Okay.
red.
Can I explain that top row? That is what the galaxy would look like normally, if it's close to it. I mean, if it wasn't moving at all.
Right?
Okay. That top row is what it would look like if it was not moving at all.
That's
Okay.
right.
Now, the middle row is what it actually looks like. And
Yep.
that's what Lee is explaining that it's very stretched out. And can you point the three and three in each row?
Yeah, so these are earthbound laboratory emission lines right here. There are these three, one, two, three, one bright and two dimmer ones. Here is that one bright one. It's shifted all the way to here, and the two dimmer ones are shifted here. Notice how it's stretched and distorted out.
Right.
That's a 41% wavelength shift, or that's a massive shift.
Yes. So that is saying that that galaxy is accelerating away from us at a tremendous speed. And that's why its light is red shifted like that.
Yep.
Okay. And so, according to CGC, the reason why galaxies are red shifted like that is because they are actually accelerating away from us in space because CGC makes the claim that the universe goes through periods of gentle expansion and gentle contraction. And
Right.
now we happen to be in a period of gentle expansion, which in CGC means that during this expansion, because of repulsive gravity, those galaxies are actually accelerating away from us. And that is why they are redshifted. That in combination with the tired light idea. So it's like two things causing the redshift.
Right.
Whereas in general relativity, they're saying the entire universe is constantly expanding. You know, the space itself is constantly expanding, and that's why the galaxies are accelerating away from us. So it's like two different explanations of the same phenomenon.
And we're over a century past this discovery, which was really in some ways first heralded by Vesto Melvin Slipher at Lowell Observatories. Here's his original paper where he showed in 2015 that most of the few galaxies that the 15 galaxies that he assayed had a positive red shift, meaning they were moving away, accelerating away, if you interpret it as a Doppler shift. And his 2017 paper had even more galaxies there with a predominantly positive red shift.
Yeah,
Hubble
so
later
pretty
came along
pretty
and
universal, yeah.
yeah, yeah, yeah. All right, I'll stop sharing you so you can continue then.
Okay. All right. So then so what that means is, and let me get back to the paper here. All right. So some of the things that, and now this brings me back to the things that Lee was talking about. So there, I lost my train of thought, but now my train is back. So what Lee was explaining about was different inconsistencies in the redshift. Okay, so according to standard cosmology, you have the entire universe expanding at a constant rate, and that's the way that general relativity describes the behavior of the universe. But when we look out at this red shifting, okay, we start noticing interesting things. Like if we look out at a certain region in space, we see, okay, the red shift there isn't exactly what is predicted by a constant redshift in that little spot. You look over in another spot and you have another variation where things aren't quite expanding the way that we thought they would. Okay, and so you have anomalous things, and as Lee said, sometimes you see two objects that are obviously near each other and gravitationally bound, yet their redshifts don't line up with each other.
Right.
Okay. And so then we start seeing all these different inconsistencies where the redshift as we look out in the universe, it is very obviously not constant. And there are all these anomalous shifts. And not only that, but the red shifts start showing a pattern, a wave-like pattern, which is what you'd expect in CGC. You'd expect to see these sort of wave-like patterns the in CGC. It's the actual acceleration of these objects. And so if gravity behaves sort of like a wave function, as depicted in CGC, then you'd expect to see wave-like variations in the redshift. Now, another reason,
Any of the oscillatory models, and I'm sorry, Vestal Melvin Slipher is his name. Slipher to pronounce it correctly,
Mhm.
sorry. And we can edit all that out, sorry.
Oh, that's all right, no problem.
Yeah, yeah. Um, Oscillatory models can have these variations, various oscillatory models where the universe oscillates can have those kind of so-called anomalies in redshift patterns.
Right, that's right. And then the other aspect, which also is in my paper, is the tired light idea, which is fairly simple in that when you're talking about very extreme distances, light loses some of its energy, and when it loses some of its energy, it becomes slightly redshifted. Now, cosmologists were, oh, I forget how many years ago, maybe something like 20 years ago, they were able to prove, and I looked at the research and I agree with it, they were able to prove that tired light could not account for all of the redshift.
Right.
Uh, and so tired light is not an explanation for all of the redshift, but in my opinion, it is an explanation for why things super far away will have a degree of redshift that comes from light just simply losing energy traveling those great distances. So some of the redshift, in my view, is caused because of tired light.
Right. And whether the tired light view holds up or not in the long term, we should give credit to Fritz Zwicky in 1929, who published a paper in the in the PNAS where he first proposed that tired light theory. Yeah,
Right. Well, thank you, Lee. That's good.
yeah, absolutely.
All right. So then I want to go over several of the images from Webb, as discussed on the show a few times now before, is that when
Yes,
the Webb telescope came online, because Webb looks further back than any telescope has ever looked, to where Webb can look, right to the dawn of the universe. Now, in my steady state oscillatory model of the universe, I claim the universe is eternal and it is forever oscillating like this back and forth with, as I said, eras of gentle expansion followed by eras of gentle contraction. And I claim that all of the matter in the universe is endlessly recycled, and that's what black holes and active galactic nuclei are in fact recycling mechanisms where everything in the universe gets broken back down to basic hydrogen. So things over time you have metals and heavier elements created, and then at the end of the cycle, I believe they are recycled through a black hole and get ejected as simple hydrogen again. Um, but in any case, let's take a look at some of these things, many of which we've talked about before, but it's okay to go over them again. I'll just go over each of the articles. Oh, I better share a screen here. First, I should share a screen and then go over them. Okay, the first one I would like to talk about, and this one I have to laugh at, okay? They're desperate to find what are called population three stars. Because if you believe that all of the universe started with a Big Bang, at that very beginning of the universe, all matter would be hydrogen or at least or at most helium. Okay, because none of the heavier metals, and in cosmology, basically we call anything heavier than helium, we call it a metal. Okay, so if I use the word metals in this context, I just mean stuff heavier than helium, but most especially, what we'd really call metals is stuff like iron or things that are very heavy when compared to hydrogen. So in the early universe, if it all was this seething cauldron of gas, then at that time, everything was either ionized hydrogen or maybe some helium. And so the very first stars had to be almost pure hydrogen. And we call these population three stars.
right.
And so when the Webb telescope came online, one of the things they were hoping to do was to look back at a time period and see a bunch of these population three stars. Because they said that that's what all the stars had to be to begin with. And then stars go through this cycle of, gas comes together, forms a star, it burns for a while, it goes nova, And when it goes nova, the pressures involved are high enough that you can get the manufacturing of heavier elements. And so to get something like iron, for example, stars have to go through several cycles of this. Like you've got to have congeal, so hydrogen gas congeal. It forms a star. It lasts however long it lasts. It goes nova. Then you make something like, let's say, maybe lithium and maybe some carbon, right? Then you go through another cycle of the same thing. All that matter congeals, forms a star, it burns, it goes nova again, and you get still heavier stuff. And so it takes like several cycles of that before you can get to the really heavy elements like iron, for example. And
Right.
so when they look back at the very beginning of the universe, they're expecting to find all these population three stars, which are pure hydrogen. And the problem was when Webb came online, they didn't find any. Okay, but they're really searching. And so in this article, I think it's just funny because they can periodically articles like this come out. They say, "Oh, we might have found one," you know. And the reason why it makes me laugh is because, if you think the entire universe was filled with exclusively these stars back at that time, you should be seeing millions of them, right?
Right.
You
Absolutely.
shouldn't be like saying, "Oh, we might have found one in this, one galaxy. There's a chance, maybe." And so they keep searching for these population three stars. And to date, they're nowhere to be found. Okay. There are no population three stars. So
Yep.
when they look back at the early stuff back there, what they find instead is this metal rich galaxies in the early universe. So at
And
a
of course,
very
when we
early
say,
time,
oh,
you
sorry,
know,
go ahead. Yeah.
that's all right, Lee, feel free.
Yeah. When we say metal rich, what we really mean is high metallicity, meaning elements higher than helium out there,
That's right. And
higher
so
than hydrogen out there. You know,
and this is what Webb is actually finding. It's like
yep.
looking at a few 100 million years after the Big Bang, supposedly the Big Bang, which I don't believe ever happened. They're finding these metal-rich galaxies, which can only happen if there's been several cycles of stars already. And
Exactly.
how can you have several cycles of stars, when you're like a few 100 million years after where you say the Big Bang is, it's just not possible.
Sometimes less than half a million uh, years supposedly after the Big Bang. So, for instance, if uh, if you go to my chapter 5, the James Webb Space Telescope discoveries are rocking the foundations of the lambda cold dark matter hot Big Bang theory. Uh, you'll find a lot of these papers where I've summarized data on several different subjects where the JWST is finding anomalies that don't fit well within the prevailing version of the hot Big Bang. Yeah,
Thank you, Lee. And then just for so everybody knows, when we use the phrase JWST, that's the James Webb Space Telescope.
right.
Sometimes we'll say Webb, sometimes we'll say JWST. And then another thing that we have talked about before, and I will talk about again. Let's see, is finding galaxies. Um, oh, I wasn't sharing. Did I stop
No,
sharing?
no, you just had it there for just a second. Go ahead and re-share it. It was
All right.
there. Yeah,
So yeah, I will share that. But just to kind of put things in perspective for this next item, when you have a galaxy like the Milky Way, um, the Milky Way takes about like 100 million years to make one revolution. Okay, and so that's the time scale we're talking about. When you're talking about something as large as a galaxy, and it has a very distinct, well-developed shape to it. This disc shape with the spiral arms and so forth. Trying to imagine that take shape is billions of years for that to take shape. You know, if
Yeah,
how can you have these trailing arms like that, which obviously the galaxy's been spinning for quite a while to be able to develop such a shape. And as I said, it takes 100 million years just to make one cycle. So a galaxy like the Milky Way obviously took billions upon billions of years to form, to develop this present shape, this well-developed shape. And
yeah, yeah.
so when Webb
Let
looked
me
in the
just add
back,
a
go
quick
ahead.
item there. Yeah, the revolution period of the Milky Way, which is a barred spiral, is 225 million years.
Oh,
So
thank you.
yeah,
Even
yeah,
more than what I said.
even worse than
Yes,
for
yes. So yeah, thanks for that, Lee. So
yeah,
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 hey, I was only like 100% off. So anyway, so it takes like 200 million years to make one revolution. Okay, so when the astronomers were going to get on with Webb, they were very excited because they expected when they looked back to right at the beginning of the universe, they expected a lot of dust and gas. They expected a lot of lumpy formation stuff, just barely beginning to form galaxies. They expected things to be chaotic and messy all over the place. And instead, when they look back, what they're seeing is, hey, it sort of looks like now. Okay. And so
yeah.
when we look at this
And
article,
uh, and some of the globular clusters, very tight old groups of old stars within the Milky Way, some of them are billions of years old. Some have argued,
I'm sorry, Lee, can you repeat that? I was distracted there a sec.
oh yeah, yeah. I mean, many of some of the oldest star populations within the Milky Way, like some of the ancient stars within the globular clusters, some of those are pushing ages that rival the supposed age of the universe.
Right. Yes, that's another thing we find. They found examples of stuff like that, like Methuselah stars out there. That just call into question the entire thing. And so when you find stuff right here locally with us that old, you know, it just doesn't. The whole thing just doesn't make sense. It doesn't add up. So here we have astronomers looking back, and fittingly. They are baffled to find a galaxy like right at the birth of the universe that has the same type of shape and disk and well-developed form as the Milky Way. And so if you're looking at something a few hundred million years after the supposed Big Bang, that is just simply impossible. Now, articles, like if you read the article, you read all these articles, you never get any standard cosmologists say like, okay, well, we got to start questioning the Big Bang, obviously. Instead, what they say is, oh, we need to question our ideas of galaxy formation. The implication being that maybe there's some sort of weird fast forward where you can go zip, zip, zip in a couple 100 million years and have a galaxy look like a modern galaxy. Okay. And so they're willing to, in my view, come up with all kinds of outlandish mechanisms with absolutely no proof other than that they need them. The only proof that these mechanisms exist is because standard theorists really want them because otherwise they'd have to question their basic assumptions. Um, and so that is another one of these things. Now, one of them that we haven't talked about before on the show, which I'm trying to find here. Let's see. These ones. Okay, this one. I keep telling myself it's the most funny of all every time I come across one of these things. But here is another one. And the Webb telescope, when it looks back at this time period, we're talking about a couple 100 million years after the supposed Big Bang. They're seeing all these red dots, okay, and they have a big problem. And I want to talk about this a little bit first. So the problem is when you see an object in space through a telescope, you've got a few candidates, like what might that object be? Okay, it can be gas, it can be dust. You could be looking at a black hole, you could be looking at a neutron star, you could be looking at a galaxy. You know, there's not a whole lot of options there. And each of these things has its own special characteristics, so that you can tag it with what it is. Now, when they looked at these red dots, the most obvious assumption, based on the characteristics of those red dots, the type of light that was coming from them, and so forth, is that they're not like a single star type object. What they are is a very distant galaxy.
Yep.
Okay.
Yep.
And so that's the first thing that just, leaps out of the data, the first assumption. It's a galaxy. But they have a problem in that if they're looking that far back, like a couple 100 million years after the supposed Big Bang, and they see a red dot like that is so super redshifted and is obviously a well-formed galaxy, that even at that resolution is so tiny, it suggests that you can look even further back in the universe. Like you could look further back a couple hundred, not a couple hundred, but several billion years further back than what you're looking right now. In other words, if we get something that had like 100 times the resolution of Webb, that thing might look like just a normal spiral galaxy, but the light that got to you from that one must have been traveling for like 16, 17 billion years. Okay. And so that would explain it.
Right.
But obviously, if you say that, what happens to your Big Bang idea? Okay.
W-
So they can't just say what it is. So instead, they have to keep coming up with outlandish explanations. And in this article, again, I'll put that in the comments. This article, goes through and explains how, there must be some black holes that are radiating light in a super luminous way, and that's what's causing these red dots, to behave this way. And so it's some weird new phenomenon, weird new combination of black holes with surrounding gas behaving in a way that we don't see in modern times. Okay. So the
That
first thing, as a scientist, the first thing you're going to ask, if you're a real scientist, is you'll say, well, you're proposing this like outlandish mechanism to explain this, right? But how do we verify that that is what's going on? Is there anywhere in the local universe where you see this kind of mechanism happening so that we can know that this type of mechanism actually exists out there somewhere? Okay, and that you're not just coming up with any old thing, which we have no way of testing, and you're saying, oh, something weird must be happening. And it's like, well, buddy, what if nothing weird's happening and you're just looking at a distant galaxy, right? There's nothing weird going on. So, uh,
that's we're full of things like that. If I may share for just a second. Um,
go ahead.
yeah. So here are, Hubble, I mean, well, Hubble is the little small, we've already seen this transition of what they thought were unusual objects just turned out to be ordinary galaxies, more ordinary galaxies, just in the transition between the Hubble and the James Webb Space Telescope. Here are some of the larger telescopes which are proposed, right?
Right,
Okay. Now, if we actually go to briefly to this chapter about James Webb rocking the foundations of the big hot Big Bang, uh, and of course I like to put it beside the James Webb beside Galileo's telescope there because it
Yeah,
actually,
that's pretty cool. How
yeah,
fitting.
yeah, two cosmological theory ball buster instruments here, as it were, and
Right, right.
and and so forth. Within this chapter, from the very time of the first public results of the James Webb Space Telescope, one can go through and see multiple papers where in fact um, the predictions are being challenged by new results, the common conventional predictions.
Yeah, it's just been a constant thing since Webb has gone online. And in every article and every paper, you have people proposing, rather than just simply acknowledging what they're seeing, just proposing outlandish mechanisms, mechanism after mechanism after mechanism. The one that Lee and I often joke about is galaxy collisions. That's one of their favorite ones. There's some weird galaxy collision that explains it.
Merger mania.
Merger mania, yes. Everything we can't explain was due to some merger that happened right before we see this. Right before the observation. Well, when I say right before, I mean several million years before. But right before the observation, we had some weird merger, and that's what caused what we're seeing.
Yeah.
So, yeah, the thing that all these mechanisms have in common is there's no way of verifying them.
And many of the supposedly interacting merger systems actually, when you examine them, they look like they're coming apart rather than merging, in fact, so
Right, right. Then there was one, where is there was one, a reionization one. Why is that one not showing up? Let me find that one. That one was also very interesting to me. So I want to find, I think that's the last one. There it is. Oh, yeah. Hmm. You know what? I'm going to have to find that article because I see that I made a mistake here. Uh, so I'll try and come back to that.
yeah.
Let me mention this one here.
Hmm.
Briefly about quasars and giant black holes. Basically, essentially, what a quasar is a giant black hole, and this is very similar. Um, and so I'll include these articles too in the comments. There's some articles about quasars when Webb is looking back to that time, it's finding the existence of quasars, which are just supermassive black holes. And the problem with that is it takes a very long time for a black hole, and especially a supermassive black hole, to form. Now, in popular conception or to a layperson, that will not seem to make sense. It's like, okay, if you have a black hole, it's got super strong gravity, okay? Doesn't it just suck things in really fast and it can just form like super fast? In reality, that's not the case because as you start approaching something with a very strong gravitational field, like, well, let's just use the sun as an example. Sometimes people say, like, can't we just get rid of all of our garbage by, launching it to the sun? Okay. Well, the problem is we are traveling on the Earth, I think something like 30,000 miles a second, something like that, or maybe I'm an order of magnitude wrong. Maybe it's something like, well, anyways, I forget. My point is, it's extremely fast. It speeds ridiculous to us. Um, and so for something to fall into the sun, it would have to be traveling slow enough that it would not end up going into orbit. That's the thesis of what I'm trying to say. So for anything to fall into a gravity well and actually be absorbed by the thing at the center of that gravity well, it has to have a speed that's slow enough that it doesn't end up going into orbit. Now, if you start dropping stuff towards the sun, unless it's on a direct beeline right for the center of the sun, it has very small relative speed to the sun. It's not just going to simply fall in, it's going to end up going into orbit. And so when you have gas and dust and meteors and planets or planetoids and stuff around a big gravity well, typically they have some sort of orbital speed going on. And so stuff doesn't just fall in rapidly like we see in the movies, around a black hole or something where it just like sucks everything in and it happens very quick. Instead, it takes millions of years for these things to accrete such a large mass. I should say billions of years. And so it's just another anomaly where they're finding these huge, massive black holes, quasars, in the very early universe, which, according to standard theory, they just have not had the time to accrete all that material. It's just not possible. And so, again, they're trying to come up with, in my view, various ridiculous mechanisms to try to explain, well, how did they manage to accrete it? So they'll say, like, they won't say Big Bang is being challenged. What they'll say was, our ideas about matter accreting into quasars is being challenged. Okay, so the stuff that we observe, like we have observed how things go into black holes or neutron stars. So we've observed that. And so they're telling us we need to question the stuff we've observed in order that we can claim that there's a hot Big Bang that we have not observed, right? And
Right.
typically that's backwards science, right? You usually go with what your observations are telling you rather than what your speculations are telling you.
So, so this reminds me, here if I share this screen here from my home page, epicycles, adding a bunch of epicycles to make the old theory work,
Yeah, that's classic, right? You can say, yeah, then they'll say that pi is just a naturally occurring thing out of the theory.
That's
And,
right.
and
Rather
of
than
course, especially rather than a specially designed thing to create pi, it's just that just sort of randomly happened from the theory, right?
yeah, you got all these extra wheels to make the motions work, rather than just, taking the ratio between the circumference and the measured diameter.
Right. That's so funny. Okay, so then I am going to try this to find this one other article.
I I wonder what some of the greats like Hubble, Humason, and Slipher would think if they had access to the James Webb Space Telescope.
It's hard to say in the sense that what Webb has demonstrated to me is that we will never escape from confirmation bias, and it's very, very difficult for. Uh, I mean, once a theory gets widely adopted and accepted, and all of the major thinkers and all of the major researchers, all of the professional scientists in a field, they're subscribing to this one thing. It is tough to break away from that. We really need, and obviously we need some tests done to just disprove all this in an undeniable way. I just keep thinking like, okay, well, after each ridiculous thing, I keep thinking like, okay, well, now they'll have to see that this doesn't work. It's just like it's just like one after the other after the other. Now, what I'm trying to find is the hydrogen lines. And actually, for 1 second, I am going to pause the recording because I want to find this and just kind of close with that. And it will take me a minute to find it. So I am going to Okay, so the thing that I wanted to, the last article that I wanted to take a look at was just about reionization. And so, what is that? Let me just explain a little bit about reionization. So, of course, in standard theory, you have this bubbling cauldron of ionized gas at the very beginning of the universe. And as things expanded and cooled, everything became neutral hydrogen. And so the universe was just, and there were no stars yet because matter had not congealed to form stars. So we call this the Dark Ages because of the fact that no stars had formed yet, and all of the universe was just drifting hydrogen, supposedly. Now, reionization happened. Well, okay, so let's go right after that phase is when all of the hydrogen started coming together into clumps, and that's when you'd first start getting these stars starting to form and galaxies starting to form. And as I talked about earlier, at this stage, we'd be expecting to see these population three stars that are stars formed just of pure hydrogen. Now, when you have uh, pure hydrogen, hydrogen, there's a certain bandwidth of light that pure hydrogen will absorb, and that is what produces what is called the Lyman alpha line. Okay. And so if you see that Lyman alpha line, what it means is that neutral hydrogen is not around because if neutral hydrogen was around, it would absorb that. Okay. And so when you go very far back in the universe, what you're expecting to see in the very earliest times is you're expecting to see um, a span of time where you do not see that Lyman alpha line. You don't see it because neutral hydrogen has absorbed it. And the problem is that when cosmologists look back with Webb, they just do not find this time period, and that's what this article is about here.
There it is.
So this article here, where is it's challenging. The telescope's latest breakthrough is upending our understanding. Now, look how they never say it disproves cosmic reionization. Right? You look back, you
Right.
don't see any evidence of this, and they don't say it's disproved. They say, oh, it's upstanding our understanding of it. They're not saying, oh, it's disproved. So they look back at this time period and they find that there is actually no evidence for this time period of what they call cosmic reionization. Um, just to make clear, we are living in a space where the intergalactic medium is ionized. What does that mean? It means that it is composed of hydrogen atoms where the electron is separated from the atom and it's all floating together in sort of a plasma. And by plasma, I mean not neutral hydrogen, right? It's charged particles. Uh, you have the nucleus of the hydrogen atom, the proton, and you have the electron kind of wandering around separated from each other. And because they're separated from each other, that's what we mean by ionized. And so far as we know, according to my belief, the universe has always been like that. And there never was a time when most of the universe was neutral hydrogen. Uh, that has
Right.
just never existed. I don't believe that's ever existed. We've always been ionized. But Webb was supposedly going to be able to look back at this time period when the universe was just first starting to congeal, and most of the universe was filled with neutral hydrogen, right? And if that were the case, we would not expect to see this Lyman alpha line. Okay.
Let me quickly show a graphic to illustrate what's being referred to with reionization here.
Sure, sure.
Yeah. So so for instance, in the lambda cold dark matter theory, which I call the new Ptolemaic system.
Oh,
Okay.
good.
Uh, 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 there's supposed to be a period after the Big Bang. Here is the microwave background radiation, the Big Bang. Here is modern times. This is supposed to be about 13.77 billion years. Reionization after the before stars and galaxies start forming, there's supposed to be a dark period when there's all this neutral hydrogen they call the dark ages. And then reionization is supposed to happen with those population 3 stars, and you're supposed to see this transition. Well, they're not finding this transition. That was supposed to happen about 400 million years after the Big Bang, roughly, you know.
Yeah,
Not
so that
there.
transition, they're not seeing it.
They're not seeing that transition. That's a problem.
Yeah, they're not seeing the population 3 stars that would start the process.
And they're not
Uh,
seing that neutral
Not
hydrogen
seeing that
predominance.
neutral hydrogen. That neutral hydrogen doesn't exist. So,
Oh
so,
well.
and rather than just say like, okay, well, that disproves reionization, they say, oh, we're just not understanding the mechanism.
Yep.
So, all right, Lee, would you like to redo that part
Sure.
that you do? Feel
Sure.
free.
I'll just go ahead and reshare that. So I'll do it'll enable, what I'll do is I'll do a little bit of repeat, just a slight
Okay,
repeat.
no problem.
So all right, just a second. Let me share, and then so here we are. Share. So as Joe was talking about, the Doppler shift, that where you've got the higher concentration of sound waves, like the siren approaching you, and then it's stretched out as it leaves you. As it goes off into the distance, the same thing happens in light.
You sounded just like a car, Lee.
Yeah, that's right. Yeah. And uh, and the same thing happens in light. Here's the laboratory emission lines on a spectrum. Uh, this bright emission line, then 2 dimmer ones, and then from the third Cambridge catalog, 295, a middle of last century, a Quasar 3C295. Here is the red shift, a 41% red shift. This bright line shifts to here. This dimmer emission line shifts to here. And this dimmer line emission line shifts to here. It's shifted to the red 41% and spread out, stretched out as well. That's an example of the red shift. Well, back at the early part of the 20th century, Vestal, Melvin, Slipher at the Lowell observatories, he published some papers. He was the first one to use redshift to measure these kind of uh, Doppler velocities, and this was the uh, the Andromeda Nebula, it was called then, but Andromeda Galaxy approaching us at 300 kilometers per second. And in 1915, Slipher published his this paper where out of 15 cases, he found that 11 of the 15 have red shifts rather than blue shifts, meaning they are moving away from us. In 2017, that had expanded to 21 out of 25 of the galaxies had red shifts rather than blue shifts. And of course, the general trend, which is now called the Hubble-Lemaitre law, was more confirmed in 1929 when Hubble published his paper showing that there's a general linear relation. It turns out that he used a lot of Slipher's data because Slipher's measurements were actually more accurate than Hubble's.
Very good.
Yep, there you go. All right, so I've done justice now to the men of the past there. So,
All right, great. All right. All right. Well, thanks for showing up with us today, Lee Greer. And I would like to thank everybody for watching. Is there anything else you'd like to add, Lee?
I think that this is one of those exciting times if one is looking carefully in the papers and at the data rather than in the confident public pronouncements of mainstream cosmologists, one will see that actually a revolution is underway in cosmology. It'll take a
Yes,
while,
I agree. So it's going to be an exciting era right ahead of us. So
right? And it has been. JWST is changing things, but even before JWST, much of the data is giving is really rocking the foundations of the hot Big Bang cosmology.
yes, I agree. All right, everybody. Well, thanks for watching today, and we will try to begin doing this monthly. And so stay tuned. Have a nice day. Bye bye for now.
Thank you.